Okay, like every space nerd worth his salt, I want to see us get human exploration out of low Earth orbit. And while I view with great interest the many robotic missions undertaken by NASA and other governments, I long to see human exploration as well. Currently, the best hope on the horizon is Starship. Its target, based on full reusability, is to reduce the current cost to orbit from around $5,000 per pound to eventually as low as tens of dollars a pound. This opens a whole new universe of possibilities. Budgets that targeted getting hundreds of pounds to orbit can now potentially get tons into orbit. But this only gets us to low Earth orbit. If we want to explore the Moon and Mars and even other bodies in our solar system, we need to climb all the way out of the Earth's gravity well. In the case of the Moon, not quite out of Earth's orbit, but the total delta V to get there and land is in the same ballpark. But by design, the Starship only launches with enough propellant to reach orbit with about 100 to 150 tons of payload. SpaceX says that if they fully refuel the Starship in orbit, Starship could reach Mars and beyond. However, by design to keep Starship's mass as low as possible, the main tanks are not insulated. Since they are filled in the last minutes before launch and the propellant is used within a few minutes, boil-off is not a real problem. But if it were to wait in orbit for many days while additional fuel is ferried up, there would be huge losses due to boil-off, especially whenever Starship is in direct sunlight, which is most of the time. One idea I've heard is using a Starship to accumulate the fuel in orbit ahead of time. That way your mission Starship could quickly transfer the needed fuel all at once and be gone. But the surrogate Starship would not have insulated tanks either, so boil-off of propellant would still be a problem. I believe what is needed is an orbital fuel transfer facility. This facility would have both double-wall insulated tanks and a sun shield. This would allow very long storage times for the cryogenic propellants and give a much bigger time window for bringing fuel/propellant to orbit. This would also allow fuel to be ready in orbit well before a mission planned for its use is launched. Now, we've all seen how fluids like water can be floated around the ISS in weightlessness, where the only force on them is the surface tension of the water keeping them in globules, which we see the astronauts playing with. But in a fuel tank, this is a problem. If your liquid is floating in the center of your tank, there's no way to force it out. If the tank was flexible, you could squeeze it out, but at cryogenic temperatures around minus 182 degrees centigrade, not many materials, if any, could be used in such a manner. So the easiest method is to rotate the tank so that the centrifugal force will push the liquid to one end of the tank, allowing either pressure or pumping to move the liquid. So let's build a facility. Since Starship has a large cargo volume, my fuel transfer facility's first module is huge. 25 feet in diameter and over 40 feet long. It will be my habitat and control center. Since it's a working facility, I will give it 2 airlocks large enough to move personnel and hardware in and out. 2 docking ports. On the other side is another airlock which will allow access to the tank farm area once installed and pressurized. Initially, solar arrays and radiators on the circumference will be adequate to provide the power needed during early construction. few days after arriving in orbit, the module is joined by first a Crew Dragon with 4 to 5 crew, and then by a Cargo Dragon with supplies. Our next Starship arrives with the backbone of the tank farm. Folded up to fit in a single Starship, it can be unfolded to form a tube 10 feet in diameter, over 100 feet long. Once installed, it becomes an additional pressurized volume for the crew and contains all the plumbing, pumps, and other controls needed to operate the tanks. Now come the tanks. 3 pairs of tanks sized so that a pair can fit in one Starship. These 6 tanks will allow the facility to hold more than one Starship's worth of both liquid oxygen and methane. The 4th pair of tanks would hold liquid nitrogen and other cryogens. To complete the rough build-out, we bring up the Starship docking fixture, which allows tail-first docking of the Starship, as well as a conventional docking adapter for the lunar version of Starship. To build the sunscreen, we will need some structure. I'm calling these elements outriggers. They provide the frame for the screen, as well as mounting points for rotational thrusters. Here we see the sunscreen is also a shield. Each panel is multiple layers, a steel outside layer and an aluminum plate inside layer. Sandwiched between is an inch of aerogel, 2 inches of woven Nomex Kevlar fabric, and another inch of aerogel. This type of shield was designed by Fred Whipple to protect NASA spacecraft from small hypervelocity objects like micrometeorites. There have been many versions, but basically it is an outer shell called a bumper, hard enough to cause the incoming object to break up, spreading the energy over a larger footprint. The fabric layer then both removes some energy and helps defocus the energy. This means the impact energy reaching the inner layer, called the liner, is now spread out over a relatively large area such that it can be stopped. While not providing total protection, it does offer a great deal, and provides shade from the sun. The resulting cylinder will also allow installation of a great number of solar panels, and a large internal volume out of the sun, which can accommodate radiators. Next, we'll be installing those and putting the facility to work.